Hello, welcome to the second part of the solutions. We were discussing the midterm solutions of operating systems and system software course. Now let us try to understand the question 6 now. Assuming all the processes have completed their execution at time unit 19. That means whatever is shown here, they all completed their execution. That means there is nothing else for it to execute beyond this particular time. Now compute the average waiting time of these processes if they all came in at time t equal to 0. That means all of them entered the system at t equal to 0. So now what is the average waiting time? I think this is very straightforward from the timeline shown here. So let me try to get it from here. All the processes come in at this time. When I say come in at that time, all of them are already available in ready queue. How many processes are there? You can see that there are 4. Now we are not worrying about what kind of scheduler being run here. So let us not try to understand about that right now. This question only talks about what is the waiting time given these processes have run during these time intervals. Now when they don't get a chance to run, they are waiting. Okay, we don't have to worry about how they have been ordered in the ready queue, how they are picked up for the scheduler by the scheduler next time. The algorithm used may be different. There may be different queues also. So we are not talking about it right now. We are only saying that given this Gantt chart, this is the order in which these processes have been executed by the CPU. Whatever may be the algorithm that scheduler follows, what is the waiting time of these processes? So you need to worry only about that. You don't need to worry about what scheduler is running. Is it preemptive or not? Maybe you will know from the timeline. If I ask you whether this is a preemptive scheduler, you need to say yes, because P2 was running for some time and then it has stopped for a while and then it has come later on. So even this you cannot predict whether it is a preemptive or not. Maybe possible that at this time these processes have given up the CPU on its own. So unless otherwise it is stated, you don't need to make a assumption there. Here for by computing the waiting time of these processes, you don't need all this information. What we need is, okay, when it came in and when it got a chance to run, and the remaining time that they were not on the CPU is a waiting time. Because if we say that it is blocked by itself, then we will not be accounting it as a blocked waiting time, because they will not be in the ready queue. They voluntarily gave up the CPU. So here we can assume that they were forced out by the CPU, by the scheduler, not the CPU. So whenever it is not running, you can consider it to be a waiting time. Okay, because no state information is given. It's all only the sequence of processes which have run on the CPU. So given this situation, how will you compute the waiting time? Very simple. Now P1 came in at 0 and started running. Now did P1 get a chance to run later on? No. And then it says that all the processes have completed their execution at time unit 19. That means P1 is still not alive beyond 19. That means it is terminated already. So from this statement, you can in fact say that the total execution time of P1 is 1 time unit, because it did not run again. But I am saying that all the processes are completed. So from the statement given, what all can you conclusively derive? You can think of it. Okay, maybe if I ask, if there is a question like this, you should be able to answer it, connecting with what is given here and what is shown as a diagram. So P1 is completed by 1 and it's not showing up later on. That means if I have to add up all the waiting time, I will have to say 0 for P1. Now how much time P2 was waiting for? Now it was running for a while. From 0 it did not get a, because certainly 0 to 1 it was waiting, because I said that all of them have come into the system at 0. That means they are in the ready queue already. So you can say that maybe I will for P1 I will add up all the things here and then we will write the sum there. So from 0 to 1, P2 was, sorry, this is P1. Then I am looking for what happened to P2 when all it was waiting. So 0 to 1 it was waiting for sure. So one time unit it was waiting. Then it was run for 1 and then again P3 got a chance to run. P2 was not getting a chance to run there. So 2 to 3 also it was waiting. So I can say that it is plus 1 assuming that they were forcibly taken out. Okay. So in that assumption I can add all of the thing because no information is given whether they are in the blocked queue or ready queue. So unless the information is not given, you cannot assume that. Then it will become much more complex to come up with the figure. So you can always say state in case if that is required. In this case, not needed, but still you can say that all of them have been forced out by the CPU, not by the by itself, voluntarily given up. So 2 plus P2 was waiting for, we are just counting the time that P2 was in the waiting during not in the CPU, but the time during which it was not in the CPU is the waiting time. So 2 to 3 it was waiting, so I have added these two number. Now when does the P2 come again? It is not coming again at all. That means the P2 is completed. Now you can actually conclusively say that the execution time of P2 is here 1 unit and here 1 unit. So 2 unit is a execution time, but we are not asking for that. We are just only waiting time. Now what about P3? P3 got a chance to run here after 2 time units. So maybe this is a thing for P3. It initially waited for 2 time units. Then it ran for 1 unit. Then again for 1 more unit it was given to the P2. So let me add that. And then again P3 was forced out and P4 was given for 1 time unit. So 1 more time unit you have to add because here 1 unit it was waiting from 3 to 4 and again from 6 to 7 P3 is waiting. Then again from 9 to 13 it is waiting. So you have to be careful about how many units are here. It is 4 time units, correct? So that needs to be added. So totally how much? You know that 8. So P3 is 8. Okay, waiting time because after this 19 it is anyway done. Now what about P4? P4 till this point till 6 P4 did not get a chance to run at all. So this is for P4. 6 time units it was waiting. Then it ran for a 1 unit and then again for 2 units it was waiting. So plus 2 and then P4 ran again. Okay, then it is got completed at 13. Looks like now you can add up all the CPU time of each processes and conclusively say that they are all the execution time of each of those processes. Now this is also 8. This 8. So this is the sum of all of them. So this adds up to 18. Okay, by there are only 4. So this is the 4.5. Okay, so this is a time unit they have been waiting. Average waiting time is because 4 processes are concerned. This is the time unit. I hope this is clear. So now let us try to see the next question. Okay, it is not related to this Gantt chart. So let me scroll this. Now 7th question, question 7. What is the significance of a thread calling pthread exit system call? Now if you have not gone through part 1 of the recording, I want you to go through that because I am going to assume that you have already gone through part 1 before coming into part 2 of this discussion. So thread is one. This is the main thread process, or let me call it as a process. Then one thread has come. Then another thread has been created. Suppose these are the 2 threads which have been created using pthread create. We know what is pthread create and how it is done. Maybe I will show you a piece of code to explain about what happens during pthread exit. Since during the linking of this libraries or when you are building an application using the pthread function calls, we link it with a pthread library. Okay, minus l pthread we say. That means this library is also included along with the executable. Now, what does this do? It actually makes sure that we have the implementation of all these processes, all these thread library functions are part of the executable. So these pthread library functions implement certain things. Pthread create helps us in creating the threads which accesses the data area of this process as well as code of this process. Now, one more thing you have to remember, code data is common to every thread created by the process, every T1, T2, T3. And of course, main thread is one which may be creating them. Now, stack is independent. Each of them have as each their own stack. So one thing I want you to remember that any of these threads having some strings in them, okay, some string is also accessible across the thread. Okay, if I have a pointer to the string, they are accessible. In that sense, normally what happens is string is a read only. Okay, you cannot modify once a string is part of made part of the executable or a program. So normally what happens is string is kept along with the code, though it's not an executable part of this. It is kept along with the code, and the threads are the program when you are executing them, they are accessing them with respect to the PC address. Okay, whatever is the program counter address, with respect to them, the strings are accessed. It's only as you don't need to understand or to be aware of this, but I'm just telling you when we are passing the strings across the when thread is passing it and the main thread is able to access it, that means it's across the whole family of these threads they are accessible. Okay, just keep it in mind because it will be useful when we talk about some of the implementation. Now let us come back to the pthread exit. Okay, so when a thread exits, there are many ways a thread can terminate. Now let me take up everything. Now when we are creating a thread, we are giving a pthread function as a function pointer. We are passing a pthread function which accepts void star and returns void star, which I explained. This function is again a normal C function. Okay, it's void star function, and void star is a parameter, and then we are having this function implementation. Now it will have maybe a return. In that case, it is a termination of this particular thread, because when the thread function returns, the thread doesn't know what else to do beyond that point, because that is the entry point. Now what happens when the main ends, main returns in a process perspective, that's the end of this program, right? When main itself ends, that's the end of the entire executable or entire process. Similarly, for a thread, the thread function returns, that's the end of that particular thread. It cannot execute anything beyond. So if it returns, okay, a thread function returns, assume, that means it is terminating without informing the pthread library. That means it is going to terminate the main thread. I am going to call it as a main thread, which is the process initially, which is creating spinning of lot of threads, and all the threads, many threads may be there. Now when one thread function exits or returns, I don't want to call it as exit, when it returns, that means it is not informing the pthread library that I am ending. That means it is going to kill all the threads also. Even if one thread returns, all the threads will be removed and the main thread also will be killed. So the entire process and everything will be killed, because one person is leaving without informing the pthread library means it has to be completed. Now before I say that one is any of these thread functions returning, even the main can return. It can spin off lots of threads and then it can return just like that. In that case also the entire thing will be killed, because nobody should come out of the execution without informing the pthread library. If it happens, then the entire family will be terminated. The entire process along with the threads will be terminated. Now that's one thing. Now what is the other way of a thread returning or ending its execution? Now void star some function, void star is a thread function, right? So let me now void void star, right? Now, what if I execute exit function call? Now, this exit function call is not a function call, it's system call. We say some message here, some parameter will pass. Now, this is a OS system call, nothing to do with the thread. Now, pthread exit is different from exit. So, when any thread function just executes exit, that is also same as a thread function returning. So, this is also not informing the thread library. In that case, this should go die. Entire process, entire thread should be killed. Now, what is the formal informed way of exiting a thread? Now, thread function, okay, it is returning void star and taking in void star. I am calling it as a thread function because to input is void star and output is also void star. Now it executes pthread exit. In that case, what happens is, and it can pass some string also. Okay, this is the pointer which is passed to the state, that any other thread. Now let me give an example of main thread or some other T1, or let me call it T1, T2. Now one of this is saying pthread exit. Okay, now the thread which is calling this, okay, pthread exit, is going to stop execution. That means that PID is going to be there, but it may be removed. It depends on the Linux implementation, but it's not going to execute anything further. Now, what happens to the main thread or any other thread which is in the family of processes or threads? Are they going to be stopped? No, because this exit is informed exit from the library, informing the pthread exit library. So what happens is the thread library keeps track of this particular thread exiting. So even though this execution is stopped, whatever status it has sent is also remembered, as well as the information that this thread has exited is remembered. Now, why should the pthread library keeps track of all the threads which have been exited using the pthread exit? Because there may be some other thread or any main thread might execute pthread join, okay, which will be explained later on. But just because I started off with the exit explanation, let me complete this also. Pthread join, what we give is thread ID as an input. Now, this thread ID as an input we give, saying that this particular thread which is executing this pthread join is interested in waiting for this particular thread ID, or the thread which belongs to this thread ID, or whichever was given this thread ID, to be exiting. That means it is waiting for it to be exited. That means this pthread join is going to make this thread which is calling this function to stop there, to get blocked there. It will be in a blocked state till the event of this particular whichever thread ID we are passing here is terminated using the pthread exit. Remember, if it exits without the pthread exit, this join also cannot be woken up because the entire thing will be wiped out, because it should be called only with the pthread exit. So that's why this is important, that a thread which is leaving formally should execute a pthread exit to inform the any other thread which is waiting for this pthread exit can be woken up. Okay, remember one thing, this pthread exit can happen prior to some other thread calling the pthread join, or it could happen after any thread calling a pthread join. But you may wonder, is it only one thread which can call the pthread join? It's not required. You can make many threads to join. Okay, so suppose T2 is going to exit, and imagine there are many threads which are there. All of them are waiting for something coming from this to be processed. In that case, what will happen is, because I said that data is common for all of them, this thread can process something and then put the results there. Then any other thread or many other thread which are waiting for this thread to be completing, exiting, they can continue further after that. So it is not required that only one pthread join can be woken up. Okay, and similarly, the order in which the pthread join is invoked is also independent. Okay, even after a particular thread has called a pthread exit, any other thread, in the same family. I'm not saying it's outside of this family of processes or threads or process and threads. If it executes pthread join, it will be immediately woken up because already the thread has exited. Or if it has not exited, it will be wait to wait. So remember one thing, not only one thread, many number of threads can be waiting on a particular thread to exit. As long as they know the thread id, they can wait. Okay, they can wait to join. A join means it is waiting for the thread id to exit. Similarly, the order in which they are executed is also not very well defined. You can be anything, it doesn't matter, because remember, all these processes and threads in this family are going to be running in parallel. So you cannot write a software in your code assuming that I will make sure that this is coming to this point before I execute this. They can all be in parallel, and you don't know which is going to be scheduled and how the cpu is going OS is going to schedule them in which order is independent. And it cannot write your program imagining that it's going to be happening in this order. That is why these functions are provided. If you want some thread to be completing before you start further processing something, then you have to execute this pthread join, which will make sure that what you are waiting for has been completing. It has completed its execution, and you can continue further. So that's how this. There are other mechanisms also there. This is one mechanism which we are aware of, and we are trying to understand it. So this is the summary of what is pthread exit and how does it impact the pthread join call, which is going to be explained in a later part of the explanation of this question. Okay, maybe I will stop here. Having explained pthread exit in detail, we will catch up in the next recording. Okay, bye bye, see you.